So laws of indices. Let's go through them and then I'll just pause the video and you can make a note of them. So let's just have a look at them first of all and just see where they come from. You'll get a chance to write them down. So they only apply if the base, and this is called the base of the number. So if I have any number, say 3 to the power 4, this is called the base number. And we're going to multiply that number by itself 4 times. That's what that means. So x is a number raised to some power a, we don't know what a is, power or index, sometimes called index, so hence law of indices. So x to the a multiplied by x to the b, as I've said already, you effectively just add the power. So there is the first law of indices. The second law, if I've got a number raised to a power divided by another number with the same base raised to a different power, I effectively subtract the bottom power from the top power. And the reason is, if I've got, say, x cubed over x squared, that's what that would look like, x times x times x over x times x. And as we've discussed already, if I've got the same number top and bottom, they can be cancelled out. So I'm effectively cancelling out each of these x's and replacing them with 1's. So that leaves me with just x over 1, or x. Subtract the powers, in other words. So that's where that rule comes from. The third rule, if you like, the order doesn't matter. If I've got a number raised to a power a here, and then I raise the whole lot to another power b, the law tells me I multiply those powers. And we can see why effectively. If I've got x squared cubed, that means x times x multiplied by itself 3 times. So how many x's have I got altogether? 3 lots of 2. 3 lots of 2. So I multiply the powers together. So the third law of indices simply says if I've got one power raised to another power, I multiply them. And now we come on to some root powers. And these are really important, these two, especially when we come on to logarithms, which we will be doing next time. That's why I've asterisked them. The root, the 8th root of x to the b. For example, the cube root of x squared. So a is 3 and b is 2 in this example. What that means is the cube root means what's the number which, if I multiply it by itself 3 times, gives this number inside here. That's what the cube root means. The 4th root means what's the number which, if I multiply it by itself 4 times, gives the number that I'm after. So for example, the cube root of 27 is 3, because 3 times 3 times 3 is 27. So that's what I mean by the cube root. Similar idea for the 4th root and so on. So I write the number that's the root, the cube root of x squared, for example, according to this rule, is equivalent to x to the 2 over 3 as a fraction. I'll rewrite that root as a fraction, so they are equivalent to each other. Oops. They are equivalent to each other. I could go on and prove why they are. This root is written as a fraction. It's to do with thinking of a number which I multiplied by itself gives me that number. So if I think of the square root, say the power is a half times a half, well, a half times a half is 1. So in other words, the number that I'm after to the power half multiplied by itself gives 1, which is the number. A bit awkward to get your head round quickly, but look at it more slowly in the textbook if you're interested in where these laws come from. But that's the basic idea of it. So I can replace a root, something like this, a cube root, with the fraction a third. So the x squared, so the squared goes on the top and the 3 underneath. I usually remember it, or teach it to people from the point of view of the root part of the number. The root goes underneath the ground, so the root goes underneath in the fraction, is the way to remember it, if you like. So another example might be, what is the cube root of x to the 5? Well, that would be equivalent to x to the 5 over 3. So I replace a root with a power, which is a fraction. And then I can carry on and use these other rules, say, to multiply them together, because I can add fractions. If they've got roots, I can add that way by adding the fractions in the powers. So this comes out to be quite a useful rule. The next one, or the last real rule, is this one. 1 over x to the a is x to the minus a. The inverse, and 1 over means the inverse, is replaced by a negative power. And again, it can be proved why that works, and you can have a look at how it works. But the thing to remember is, if I've got 1 over x to the a, I can replace it with x to the minus a. In other words, 1 over x cubed is equivalent to x to the minus 3. So the minus means the inverse. So those are the laws of indices. And I'll just pause this video while if you want to write down those 5 laws of indices. I'll tidy it up, get rid of all this other stuff. So finally, any number to the power 0 is 1. If I think of any number, say x cubed, I could write it like that, divided by x cubed, well, effectively, I'm replacing each of the numbers top and bottom by a 1. So I can cancel them out, in other words, and replace them with 1s. 1 over 1 is 1. And it doesn't matter what x is, if I've got the same power top and bottom, I'm going to have 1 as the answer. And if you think about the second law of indices, x cubed divided by x cubed is x to the 3 over 3. 3 minus 3 is 0. So anything to the power 0 is 1. And that's the proof. Worth remembering that when you find out if I've got a 0 as my power, what does that mean? 1. Whatever x is, it doesn't matter. Okay, so if we... Oh, and finally, if it's not obvious to you, if x is on its own, then it means x to the power 1. So if you want to make a note of that, it might be worth doing that too. So if it's just x, that means x to the power 1. So with that in mind, let's have a look at a few examples. X to the 6 times x cubed would be x to the 9. Don't necessarily need to write these down, they'll be in the video just to look at them. How can I rewrite the cube root of x squared? X to the 2 over 3. How can I rewrite 1 over x to the 5? X to the minus 5. And inverse means negative. Incidentally, if I had something like this, 2 over x to the 5, I think of that as 2 times 1 over x to the 5. They are the same thing if you think about it. 2 over x to the 5 is the same as 2 times 1 over x to the 5. So that's actually 2x to the minus 5. So in other words, if I've got a number on the top, that just stays there. And again, the inverse tells me if I've got x to the 5 underneath, it can come up to the top effectively, and I put a minus sign there. Oh, that one I've done there. I was thinking too much. This one, 3 over the square root of x cubed would look like that. Three times the inverse of the square root of x cubed is how you think of that. 3 times the inverse of the square root of x cubed. Often when we've got the square root, we don't put the 2 in. So if there's no number outside the root, that implies it's a 2 square root. So you might see that, no 2 here. And so then you'd replace this with this, and then you think, okay, inverse is the negative power, but I can replace the square root of x cubed with x to the 3 over 2, so minus because it's an inverse, and then the 3 stays in front. So that's a bit more awkward. Those of you who've done calculus with me last year will know that to be able to use calculus, the rules of calculus on numbers like this, or expressions like this rather, we need to replace this with this to be able to use the laws of calculus, so it's important to be able to do it. In the textbook there are simplifications like this. Simplify that. So to do this I would have to add up the powers of all the ones where the base is the same. So the a's, I can add the powers. What's a half plus a sixth? So I need to be able to add fractions. Base is b, I can add the powers. What's 2 plus a half? C to the minus 2 times c, I add the powers, remembering that if there's no power that means c to the power 1. So for this one, a to the half plus a sixth, b to the 2 plus a half, c to the minus 2 plus 1 is how I'd think of it. So then, what's a half plus a sixth? I'd convert a half to 3/6. Think back to how you add fractions. I can only add fractions if the bottom number's the same. So a half is 3/6. 3/6 plus 1/6 is 4/6. If I say that. Plus 2.5 I could write. 2.5. And if I put it in a calculator to calculate something, I would put 2.5. But I think of that as 2 whole ones is 4 halves, plus another half is 5 halves. I'd write it like that, actually, as the improper fraction. That's b to the power of that. And then finally, c to the minus 2 plus 1 is minus 1, isn't it? 4/6 comes down to 2/3, so I can replace that by a to the 2/3. Plus b to the 5 halves plus c to the minus 1. So I could write that. And then if I really wanted to go further, I could think, oh, well, actually, that's a root, isn't it? That's the cube root, the first one. Because of the laws of indices, that fraction there, that's the root. So I could replace that with the cube root of a squared with a 2 at the top. What could I replace the second one with? Square root of b to the 5. The square root of b to the 5. Because it's a square root, I don't need to put the 2 outside the root sign. What could I replace c to the minus 1 with? 1 over c, because it's the inverse. You might or might not want to do this, but they are the same, and seeing that they're the same and being able to do this, it's important to be able to just play around with these things, to be able to add fractions, to be able to write them in different forms and recognize that they are the same thing. It's a useful skill, so practice it. And there's exercises in the textbook that allow you to do that. We're multiplying the numbers, which means we add the powers.
Yeah, I know, but when it goes further down, when you put
Yep.
plus, you've got 85 for it.
Oh, yes, you're right. Sorry. You are multiplying, so that plus shouldn't be there. Yes, you could do. So now I could go, thanks for spotting that, yep. So I could write that as the cube root of a squared times the square root of b to the 5 over c if I wanted to, yep. Yep, thank you. Wouldn't necessarily want to, but I could, and seeing that they're all the same is important. Let's look at this one for a minute. Really, I'm going through some examples that are going to be useful to you when you come to the exercise. I'm trying to preempt problems you might have. I want to talk about fractions again for a second. Look at that fraction, 2 plus 3 over 4. That's the same as 5 over 4, because I can add the 2 and the 3. However, I also recognise that that also equals 2 quarters plus 3 quarters. I can split the fraction into 2 over 4 plus 3 over 4. They are all the same as each other. 3 different ways of saying this. I can think of it as 2 plus 3 over 4, or 5 over 4, or I can split it and write it like that. And thinking of the fraction in those 3 ways helps when trying to simplify things like this. I want to try and cancel out an x, but I can't because I've got 2 terms on the top. I can't just cancel that x with that x because I've got both of these terms are divided by xy. So I have to actually use this and split that into 2 terms. So to simplify this, I would write x squared y cubed over xy plus xy squared over xy. So this becomes this. I split the 2 terms. Now I can cancel. I've got an x on the bottom and 2 x's on the top, so I can cancel one of the x's on the top, leaving just 1x. I can cancel that y, replace it both with a 1 by the way, with one of the y's on top, so that leaves just 2. So I can take one off that power on the top. That's what I'd do, but I'm thinking about that being y times y times y. So I'm cancelling one of them out, leaving just y squared. Similarly here, x was cancelled and replaced with 1's, and that y goes into that, so I'm left with just 1y. So all this lot comes down to x y squared plus y. So to be able to simplify, I have to split the fraction. Simplify using the laws of indices. I'll pick this one because we're going to use the second law of indices, but I've got to be careful. Can anybody see where I've got to be careful and why? The problem is this minus 2 at the bottom. So let's look at it. I've got a cubed over a, which is a to the 3 minus 1, because I can think of the a underneath as just being a to the power 1. The b's, I've got 2 minus 1, because I'm subtracting the powers because they're divided. But the c's, as been pointed out, is 4 minus 2, which is plus 2. So be careful when you're using the law of indices there. If you're subtracting a negative, it becomes a positive. So this comes out to be a to the 4, b, c to the 6. Not b to the 1, because 2 minus 1 is 1, so we don't put the 1 in. So now If you look at problems on the laws of indices, again in that chapter 5 you'll see the laws of indices. There's exercises here and the solutions are in there so you can check them out. I just want to point out this particular one, number 2. Every time they come out with the new edition, they've still not corrected this error. There is a C there in number 2, and when you get to it, if you get rid of that C, I think it works, but as written you get the wrong answer. So just bear that in mind when you get to number 2 in this exercise. You might not get the answers that's in the text, and it's their fault, not yours. Okay, I'm going to stop that there now. Now I want you to just practice those basic laws of algebra, chapter 5, chapter 8.